Program visualizations reveal how code executes. They can help programmers to debug and write code, as well as to build useful mental models. But these line-by-line program visualizations differ from how programmers communicate code. Programmers regularly use visualizations that span many levels of abstractions, such as through handmade diagrams, flowcharts, and animations. We find three key design patterns underlying these visual representations. 1. Visualizations should aggregate operations together into key steps. Here, the inner for loop of insertion sort is aggregated over to show the key invariant that insertion sort builds a sorted list by inserting elements to the start. 2. Repetitive operations or structures should be abbreviated. For instance, here the first row computes the average, and then the rest of the rows compute their average synchronously. Finally, an overview should be provided of the program's execution to help infer overall patterns and contextualize the output. We instantiate these design patterns through CrossCode. We take the user source code as input and generate a skeleton representation of the control flow, as well as a view of the data. Users can interact with these representations to flexibly navigate through the program execution. Let's walk through an example. Here we have a quicksort algorithm. Let's use CrossCode to inspect its execution. We can click on a step to navigate to it. Items colored orange mean that they were read from, and items colored blue mean that they were written to. But our algorithm doesn't seem to be working. Some of the items are getting dropped. To find out what went wrong, we can step into the function call by control-clicking on it, and navigate through its substeps by clicking through them. It looks like after the for loop, the last element is not getting inserted. Let's expand the loop. So, the first iteration inserts the first item, the second one inserts the second item, and so on. But there should be one more iteration. And so this condition terminated too early. Let's fix that. Okay, so none of the items seem to be missing anymore, but 9 and 8 are in the wrong order. Let's see what happened. Here, L and R should have been sorted, but while L is sorted, R isn't. Let's expand R's call expression. And again, we notice that 9 and 8 are out of order. Let's expand one more time. So, the list 9 and 8 seems to be hitting the base case, but a list of 2 elements is not always sorted. So, let's fix the base case. And now, the quicksort algorithm works correctly. So, how is this made possible? CrossCode uses the program syntax tree to structure its execution. Unlike line-by-line debuggers, CrossCode allows users to flexibly switch between these levels and provides context to where the user currently is. However, there can be a multitude of possible abstractions and steps. Presenting all information all the time does not scale. CrossCode uses 2 mechanisms to help manage complexity. 1. Abbreviations, which collapse substeps together. In a for loop, iterations after the first one are abbreviated. This can be expanded by clicking on the abbreviations, and all abbreviations can be toggled, effectively unrolling the for loop. Function calls can be similarly abbreviated, providing ability to view long call stacks without an overwhelming amount of information. The second technique uses compact forms. These provide a zoomed-out overview of the execution without having to abbreviate or lose any information. In sum, CrossCode bridges the gap between high-level representations often seen in diagrams and animations and the low-level representations used by existing program visualizations. In doing so, it enables new workflows to debug and communicate program behavior.